Okay, let's start. Good morning. So today we are going to see the last part of the network layer, which implies an analysis of the more detailed analysis of IPv4 protocol, which means the format of packet headers and some specific functions. And then we will give a short look at some accessories that are control and management plane protocols, which we have already introduced, and they are supporting IPv4 on the data plane. So let's start with IPv4 protocol. As we know, the service offered by this layer is, by the protocol in this layer, is connectionless. So it is designed according to the packet-oriented paradigm or datagram-oriented paradigm. And datagrams are independent, so they can be, for example, routed on different routes from the same source host to the same destination host, because each packet is an individual entity which is managed by the routers on the way to the destination. The service is completely unreliable. It's only best effort delivery. You don't have guarantees of success. You don't have error recovery mechanism. You don't have packet reordering systems, and so on and so forth. So we say that, as we already said, the routing is based on a universally recognized address, and this is the first function that is performed by IP. We have already went already into the details of address assigning and the forwarding mechanism. The other function that is still to be explained is fragmentation and reassembly. So packets, as we will see, may be fragmented into smaller packets when we have some issues regarding layer 2, and in particular the limitation of frames, layer 2 frames in terms of payload. The information units, as you know, are called IP datagrams or IP packets. They are composed by a header and a payload, as we are used to know. The payload carries data. In this case, data can be anything that from the upper layer protocols, and in particular segments in case of TCP or UDP, or if the protocols that are using the packets are different, it is not necessarily limited to UDP and TCP, you will have other data structures, and we will see some example very soon. We don't have any mechanism to recover errors. However, we have error detection, and error detection is only limited to the header of the packets. So the IP protocol performs a error detection on the header, and in case a header results affected by errors, the packet is obviously discarded. And there is a error reporting mechanism. So the error is notified. No action is taken to correct the error, but still we have the error notification. And in particular, this notification is carried out using the ICMP protocol we are going to talk about. Another function is the limitation on the lifetime of the packet. So all the packets have a mechanism so that routers can understand the age of the packet. That means more or less the time that has lapsed since the packet was generated by the source host. And when this age overcome a threshold, the packet is discarded. And this is important to avoid, for example, circular routing or packets that are going indefinitely into the network if there is route mismatching. And this mechanism is based on the time to live that also we are going to see. So this is the IP packet. You can see that it is divided by header and data. That is still in Italian. The packet have a maximum length that is 65,500 and something byte. The minimum length is obviously the minimum length of the header. Okay, so if you have no data, it's possible. This is possible. You can have an empty payload. Still, however, you must have a header. And also the header is has a variable length, and the length can vary from 20 bytes to 30 bytes. And the variability on the header length depends on the optional fields. So if you have optional fields, then the header is longer than 20 bytes. If you don't have any option, the header will be 20 bytes. So 20 bytes is the minimum size of the header, and it's also the minimum size of the IP packet. As you can see, the header is usually represented just graphically as a sequence of rows. Each row is 32-bit long, and this is to adapt to the IP addressing mechanism, so IPv4 addressing mechanism, where IP addresses are 32-bit long. And also the division, the partition between the header, the different fields reflects this type of size. So each line is 4 bytes long, and you can have in the basic header 5 lines, so 5 rows. This makes 20 bytes as a minimum length. Now we are going to go through all the fields and I will explain what is the function of each of these fields. This is just what. Remember that this is only a graphical representation. In the reality, as for hosts and routers are concerned, the IP datagram is always a sequence of bytes. Okay? There is no actual division into rows. So let's start from the first field, which is version. That indicates the version of the IP protocol, and currently can have only two values. There is a code for IPv4 and another code for IPv6. This field is used mainly to understand if a packet, when it arrives to a router or a host, let's say to an IP interface in general, can be managed or not by that interface. So if the packet was generated as an IPv6 packet and it arrives to an interface which only implements IPv4, then the packet must be discarded. It cannot be managed, and also in this case a notification will be sent to the source of the packet saying that the packet was discarded. So this is why it is important to have this field inside the packet at the beginning. Yes.
Why would we use 4 bits if you can only assume you can only get 2 values?
Because it is assumed that there will be other versions of IP in the future. Then we have another field of, again using 4 bits, which is the header length. and this indicates the header, the length of the header expressed in 32-bit words. So the number that if you want the size in bytes, you have to multiply the number that is contained in this field by 4. Okay. For example, 60 bytes is the maximum for a header. It corresponds to an H length of a value of 15. Okay. This is why H length is only 4-bit, because the maximum size in IPv4, this is only for IPv4, remember, is 60 bytes. The minimum value of H length would be 5, because 20 bytes is the minimum size. Then there is the total length, that indicates the total length of the packet in byte. It is a 16-bit field, so it means that this also set the maximum, the upper boundary, to the length of the packet in byte, which is 2 to the 16. And so if you subtract the size of the header from this value, the size of the header converted into byte, of course, then you have the length of the payload. Then there is a type of service. This is a strange field that was there in the header since the beginning of IP, but in various years it underwent several changes in terms of meaning. And currently it is used with this subdivision into subfields. One is called differentiated service code point. The other one is called explicit congestion notification. And in the first field you find you can mark or label a packet with a certain category of quality of service. So, for example, if you have a value to label the packet as expedited forwarding, this means that this packet should always be forwarded by the routers, even with lack of, I mean, even if the router has a very full output buffer. So in this case, with the expedited forwarding, it is expected that the router will treat this packet in a prioritized way, letting it overcome other packets that are in the queue. Assured forwarding means that the packet will be delivered according to the first in, first out rule, but it will always be delivered in any case. It cannot be discarded, and so on. And these, so all these codes are to label the packets according to a certain quality of service requirement. It should be noted that not necessary routers support these differentiations. So most of the routers don't adopt these prioritized policies to manage their buffers. Okay? Most of the routers just ignore what is written in this type of this TOS field. So this is why it was also used for different reasons. Because it entirely depends on the router implementation if this field is meaning or not. And explicit congestion notification is a new mechanism that was introduced to enhance the congestion control. So without instead of relying only on layer 4 with TCP, in this case we can do some at least congestion notification operation in layer 3, so that the hosts are notified when a router along the path from the source to the destination is experiencing congestion or is going to experience congestion. It depends then on how this field is used. Then we have protocol. The field protocol is used to understand what protocol is exploiting IP in order to transfer data. So basically, regards the content of the payload of the packet. So in the payload of the packet, in this field tells what kinds of data is carrying. And the value that is written in the field basically is related to a list of possible protocols. These are the protocols that can exploit IP to transfer at layer 3. For example, you find TCP and UDP, as we said. You find also ICMP, which we will talk about, which is a management protocol, and for example OSPF, which is a routing protocol. They all exploit IP, directly IP, in order to carry data, and so OSPF and ICMP do not use layer 4 protocol. They directly send data on IP datagram. So these values are like service access point markers or indicators that tells what is the protocol, what is the interface used by between layer 4 and layer 3. Time to live is the field that is implementing the limitation on the lifespan of a IP packet in the internet network that I introduced before. It's a field that is set to a certain value by the source of the packet, and then it is decremented each time the packet is managed by the router. When this field time to live arrive to 0, then the packet is discarded. For example, here the time to live is initially set to 250, then it is forwarded through a certain number of routers, and here we find the same packet with a time to live equal to 2. This means that it was managed 248 times before this step here. The packet is forwarded to another router, and the time to live arrives to 1. A second router, the time to live arrives to 0. At this point, before being forwarded to an output interface of this router that sets the time to live to 0, the packet is discarded. And the packet is discarded, as we said, a notification is sent back to the source in terms of an ICMP message, so exploiting ICMP protocol, and this notification is a time sealed, so it means that the packet was discarded because time to live has arrived to 0. Yes?
This is not real time.
No. In the
just a maximum number of routers that the packet can travel through.
Yes. In the past, time to live was related to real time. So in the past, it was set to a value that I think was a time in milliseconds. So the packet had a certain time to get out from the network, and it was updated by the routers according to an evaluation of the time that was really passed from since the packet was generated. But if you use that mechanism, there must be a global synchronization somewhere. Okay? So the blocks of the routers should be synchronized. And this is not very difficult to achieve. So then they started using a decrease of 1 unit each time the packet is processed by the router. Okay.
What if the network between the sender and receiver gets more complicated and more routers are added?
Usually, this the initial value to which frankly is set is an estimation of the number of hops. So 250 is fair. So usually it's set to something like 250 because it's very difficult that you have more than 250 hosts, even if you cross internet from Asia to the United States or something like that. But of course, when the host sets this value, it should guess more or less what is the maximum length of the path. And to do this, we will see just in a minute that there are some protocols that can tell the source what is how far is the destination in terms of number of hops. Next is fragmentation. So we have a certain number of fields in the headers that are used to manage fragmentation. And so we must introduce this operation. This operation becomes necessary when the packet is transferred on a link that is a logical link on at layer 3, so at the IP layer, but as you know, corresponds to a layer 2 network. Okay, so the packet is always transferred from a router to the next using a layer 2 network that is supporting the forwarding mechanism of the packet encapsulated into a frame. Okay, in order to be transferred at layer 2, the packet must be encapsulated in a frame. And it may happen that since the packet has a variable length, as we have seen, it may happen that the frames that are used on a certain link are too short, so they're not able to host all the packet, the entire packet as a payload, because the IP packet becomes the payload of layer 2 frames. So if there is a limitation that is due to the layer 2 protocol adopted on a certain link, which limits the length of the payload of the layer 2 frames to an extent that is less, is not sufficient to carry the entire original packet, then the packet must be fragmented. Otherwise, it will never be able to go through that link. Okay? And so this is an operation that is supported by the IP protocol, so at layer 3. And in order to fragment the packet, the original packet, which is an IP datagram, is converted into a certain number of shorter datagrams, which, however, are always IP datagrams themselves. So each of them has a header, which is an IP header. And then the generated fragments then travel as independent IP datagrams until the destination. So the destination, however, must be able, which is a host usually, must be able to reconstruct the original packet before delivering it to the upper layers. So layer 4 must not be aware of what is happening at layer 3 in terms of fragmentation. So if layer 4 delivered a certain segment that generated a large packet, the receiving host, the layer 4 entities of the receiving host, should get the original fragment, the original segment, let's say, intact, so as a single protocol that. And this is why at the host we have to do reassembly operation in case there was one or more fragmentations while the packet was traveling. This is another way to explain the same concept. Here you have this network. As you can see, the LL here stands for data link, so layer 2 entities. In this case, can host a large payload in the layer 2 frames. Then we arrive here, and in this network B, the frames are shorter, so we have to fragment the packet. Fragmentation is carried out by the IP layer, so that now in this case the implementation of layer 2 will get only shorted packets that stays into the frames. This is a list of protocols of layer 2 protocols. With each one has a typical MTU, which means maximum transmission transfer unit. The MTU is it measures the length of the payload, maximum length of the payload of the frames, or layer 2 frames. And here you can see that an MTU must always be able to host an entire IP datagram. Otherwise, we have to do fragmentation. We have already met this concept while we were talking about the maximum segment size in the TCP protocol. And actually, I anticipated you that the maximum segment size value is a way to avoid fragmentation. If you are able to make segments shorter, so that you are sure that from the source to the destination, the segments that are generated will fit into an IP datagram that will fit into all the MTUs of the networks, then fragmentation is not needed. So if you are able to act at layer 4 by choosing a suitable maximum segment size, you can avoid fragmentation. But this is not always possible, and so fragmentation is a mechanism that is there, and it is contemplated by the IP protocol. For example, Ethernet, which is, let's say, the most common technology at layer 2, has frames which can have a length up to 1,518 bytes. Since the header of the frames is 18 bytes in Ethernet, this means that the maximum payload size, which is the MTU of Ethernet, is 1,500 bytes. Okay? So usually fragmentation is necessary if you are exceeding 1,500 bytes and you have Ethernet interfaces on the way. So what happens in the fragmentation process? Before delivering the packet to the lower layers, IP divides the packet into pieces, which are called the fragments. However, each of these pieces is a full-fledged IP packet, so all the pieces must have their headers. Each fragment must have its own header. Fragmentation, it can also occur in a recursive way. So it may happen that fragments that are traveling after a first fragmentation process meet another link with even a shorter MTU. So each fragment should be fragmented again. Okay? And this is possible. Then when you have fragmentation, you need reassembly, and reassembly is always carried out by the destination host. So all the fragments, once they are generated, they arrive one by one to the destination host, and you don't do a reassembly by routers, but only by the final host. Of course, in order to perform this reassembly operation, the destination host must be able to identify all the fragments that were originated by the same original IP packet, and also the host must be able to reorder the fragments. Okay? In principle, since each fragment is an independent IP datagram, fragments can arrive to the destination out of order. So they must be reordered, identified and reordered. So this is why we need a certain number of fields in the IP packets, in the headers of the IP packets, to support this fragmentation operation. And the fields involved are the following. First, there is this fragment identification field. So each packet that is generated by a host always has a certain number that is written here as identification, which is usually a number that is randomly selected. If the packet is fragmented on its way, this identification is repeated identical in all the fragments. So packets that arrive to the destination with the same fragment identification value, they form a single original IP packet. And this is a 16-bit long field. Then we have this fragment offset, which is a 13-bit long field, and this is used for fragment sorting, fragment reordering at destination. Since it is a 13-bit field, it can contain a limited number of values, and so the trick was to number all the bytes of the original packet, and here I mean the bytes in the payload of the original packet, from 0 to a certain number, and the fragment offset field is generated by looking at the numbering of the bytes, and by dividing the number by the byte number by 8. So this is equivalent to measure the payloads, the pieces of payloads in unit of 8 byte words. This fragment offset field identifies the content of a fragment by assigning to this fragment offset field the number of the first byte which is contained in the fragment, referring to the numbering of bytes in the original IP packet, and dividing by this value by 8. We are going to get back to this because it's very difficult to explain, but with an example is much easier to understand. For example, here we have a packet of 2000 of a payload with 2000 bytes, and if we split it into two fragments, each one will have 1000 bytes as a payload. So the first fragment will be identified with a fragment offset value of 0, because the first fragment takes the bytes from number 0 to number 999. Okay. These are the bytes in the original packet, which are contained into the first fragment. So fragment offset into the first fragment is 0. Fragment offset into the second fragment is equal to the number of the first byte that falls into the second fragment, in this case is 1000, because the first contains from 0 to 999. The second starts with byte number 1000. And then we have to divide it by 8. Okay. So the fragment offset value in this case would be 125. Is it clear, more or less? We will get back with a complete example. Then we have the 3 bits of the flag. The first bit is not used, so it's reserved for future uses. And then we have other 2 flags which are related to fragmentation. The first one is called, the last one is called M, and which stands for more. And this fragment, this flag is set to 1 in all the fragments except the last one. In the last one, it is set to 0. This flag allows to recognize what is the last fragment of a packet. And then the first flag is called the D, that stands for do not fragment. And it is set to 1 each time we don't want the fragmentation to be applied. So if a packet is generated by the source and the source decides to set the flag D to 1, it means that this packet will never undergo a fragmentation operation. What happens if the packet does not fit into the MTUs of a certain link between the source to the destination? In this case, the fragment is the packet is discarded. Okay, since it is marked with the do not fragment flag set, instead of fragmenting the packet is discarded and a notification is sent back to the source. So these are the two flags that are involved in the fragmentation operation. Now let's consider a complete example. So imagine that here we start with a certain packet. The packet contains a payload of 4,000 bytes. Okay. Well, remember that you always have to number the bytes only in the payload. So byte numbering does not concern the header, only the payload. So this is in this yellow box represents the payload of the original packet. You can see the byte 0 is the first one, and the last one is 3,999. Then this packet has to travel across a network, and we know that at a certain point it arrives to a link with an MTU equal to 1,420 bytes. So remember that the MTU is the size of the maximum size of the payload or the data field of the layer 2 frame. So it means that this is also the maximum total size of an IP packet which is allowed to be encapsulated in that frame. Since here we have to apply fragmentation, so we assume that the D flag is set to 0, so we can fragment the packet. We must first of all understand how many fragments are generated in this case, and you have also always to consider that the number of fragments, that each fragment will contain a maximum number of bytes in the payload, which is not exactly MTU, okay, but is MTU minus the size of the header, okay, because MTU is a limitation on the total length of the packet, but from this limitation we have to understand what is the limitation on the payload of the fragments, and so you have to subtract the size of the header. Okay? In this case, we can assume that all the headers have no optional fields, so the headers are the minimum size possible, and the minimum size of the IP header is 20 bytes. Okay. So the maximum size of the payloads of the fragments is 1,400 bytes, okay, 1,400 bytes, because it's MTU minus the header. So how many fragments we have to generate? We have to divide the original length of the payload by this number that we have calculated, in this case for 1,400, and then since we can only generate an integer number of fragments, obviously, we have to take the smallest integer greater than this ratio. So in this case, we will generate 3 segments, okay? Because we have to take it's 4,000 divided by 1,400, is 2 dot something, and so it means that we generate 3 segments. So when we generate the segments, we will put in the first segments the maximum possible payload, and then the last segment will get what is remaining, okay, which is usually shorter or equal to, but usually shorter than the maximum possible payload. So the first 2 segments in this case will have will take 1400 bytes each. The last segment will take what is remaining. So if you have 1400, it means that the last segment will start from the payload of the last segment will start from byte number 2800 and will end with byte 3900. Okay. So you can immediately also write the offset value for the 3 segments. The first one has an offset 0 because it starts from the first byte of the original payload, which is 0. The second will start from byte number 1400. So the offset is 1400 divided by 8, which is 175. The third one starts from byte 2800. The offset value is 2800 divided by 8, which is 350. Okay, this is, and here you can see also the 3 payloads labeled with the starting number of the number of the first byte and the number of the last byte. So when we have to build the fragments, each fragment has a header. This is the header of the original packet. The relevant field, only the relevant fields are written here. As you can see, when you have a packet which is not fragmented, the more byte is set to 0 because that is the first and the last fragment. And here you can see also an ID, the packet ID, and this is the total length of the packet, which is 420 because we have the payload plus 20 bytes of header. And obviously when you don't fragment anything, the fragment offset is always set to 0. Then these are the 3 packets that are generated, the 3 segments that are generated. So the first one, you can see that all the 3 segments have the same ID because they are originated by the same datagram. The first 2 have more set to 1, the last one has more set to 0. And the values of the fragment offset are the ones that we have calculated before. The lengths are 1420 for the first 2, okay, and this is the values of that we have calculated before. So the length is 1420 for the first 2 packets and 1220 for the last one. Okay, and then here we have the fragment offset and also the first and the last byte of the packet. Then we assume that the second fragment, which travels a different path from the other 2 fragments, which is possible because they are all IP datagrams, so they're free to take different paths. So the second fragment must be fragmented again, because in this case it crosses a link with an MTU equal to 820, so it's shorter. And we have to repeat all the processes that we have went through in the previous case. So we have to calculate how many fragments are generated by this new fragmentation, and we have to write the headers of these 2 fragments. So the first fragment, So this is the total length of this fragment number 2. This is the length of the first fragment 2.2 that is generated. It goes from byte 1400 to 2199. So it means that the number of bytes that are contained here in this first payload is 800, because it's the maximum allowed by this MTU, and the total length of this packet is 820, because you have to consider also the header. Then the second fragment will take bytes from 2200 until 2799. So the fragment offset is in this case 275. Notice that the fragment offset of this first of fragment 2.2 is equal to the fragment offset of fragment 2. Okay. And okay, then the fragments that traverse and arrives to the destination will be fragment 1, fragment 2.2, fragment 2.1, and fragment 3. And the destination host will put them together in order to build the original datagram, which is this one. Okay. So this is for fragmentation, and there are some exercises where you have to calculate what happens when you have to fragment a certain packet, but it's not very difficult. About options, which are the last part of the header, in IPv4 we have the possibility to add optional fields up to a maximum header length of 60 bytes, and these options are used for different purposes. They can, for example, convey information about the route, about timestamp. So if you want to write the time when a packet, and this is not time to leave, but is the exact time of a clock when the packet was sent, that can be compared to the time when the packet arrived to the destination. And it can be also used to perform source routing. So basically you write in the packet from the source to the destination what will be the route that the packet will have to cross. But most of these fields nowadays are not used anymore, and most of the routers don't take any action if they find an optional field. For example, source routing, you can also write a list of routers that the packet should cross, but when you send them the packet in the actual networks, it will not be routed on the basis of this, unless you configure the routers to enable source routing. But in this case, but you have to be the manager of all the routers that the packet is crossing. So we will not go into the details. These option fields can have different formats according to the specific field. There are some fields that are shorter than 32 bytes. So in this case, you have to insert these green boxes, which are basically padding, in order to make the total length of the header always an integer multiple of 32 bit. 32 bit. So this is a scheme of the implementation of an IP entity, an IP protocol entity inside a network interface. Okay, we don't go into the details of this. So let's now switch to the other protocols that are related to IPv4, or IP in general, let's say. So the first one, these are the protocols. This is the general scheme. So you can see that IP is carrying information coming from layer 4, but it can also it have to relay on these protocols in order to work. And so the protocols that we are going to look into are is ICMP, which stands for Internet Control Message Protocol, ARP, which stands for Address Resolution Protocol. RAP is the reverse version. We will only mention it very quickly. And then DHCP. DHCP, Dynamic Host Configuration Protocol. So the first one is used more as a management and error management, so exception management and not configuration but management protocol to notify exceptions and perform some specialized say error handling task. The second one is used to discover the MAC address that is corresponding to a specific IP address. So it is used to write the famous ARP or MAC tables that we have already introduced talking about forwarding. And RARP and DHCP are basically used for the same purpose, which is to dynamically assign an IP address plus some more informations to an interface using a centralized server. RARP is not used anymore, but the DHCP is used for this purpose. So let's talk about ICMP. We don't go into the details of all the possible messages that are used with this protocol, but just the most important one. So ICMP is a protocol to carry messages, usually between routers and hosts, or host and host, and sometimes also from router to router, but this is not very common. It is a part of the IP protocol, but however, ICMP is using IP to transport messages. So ICMP messages are directly encapsulated into the payloads of the IP packets. Okay. So it's a user of IP, even if it is also an accessory of IP. The ICMP message is, as usual, a combination of a data segment and a header. So this ICMP message, header plus data segment, becomes the payload of an IP datagram, which then in turn becomes the payload of a MAC frame or layer 2 frame in order to be transferred from one router to another, as we have seen. So once the ICMP message is encapsulated into an IP datagram, then the datagram is transferred as a normal IP packet. This is the general format of an ICMP message. As you can see here, there are two fields that identify the type of message. So they are used to identify what is the type. There is also a field to perform a checksum internal to the ICMP message. So this checksum is not related to the IP datagram, but only to the ICMP message. And then we have another part which is used as a header, and which can be variable according to the type of message, and then a part with the possibility of carrying also data. And there are two families of ICMP messages: error reporting messages and query messages. And basically, error reporting messages are generated by events. So when a certain event occurs, either in an intermediate router or at the destination host, then an error reporting message is generated. And usually these error reporting messages report errors to the source of the packet. So to the source, the interface which generated the packet. Query messages are instead, let's say, proactive, and they are usually a combination of a request and a reply. They are always a combination of request and reply. So there must be an interface which specifically sends a request and receives a reply from another interface. So as we see, as we have already mentioned, IP does not correct errors, but reports about errors. And usually errors are notified to the source of the IP packet that caused the errors. Most frequently, the source is an interface of a host, but it can also be an interface of a router. And these are the most common events that are managed in this case. Destination unreachable, time exceeded, parameter problem and redirection. There is also source quench, but it is not used anymore. So time exceeded is generated when we have time to leave, which arrives to 0, and the packet has to be discarded. Destination unreachable when the destination is not able to manage the packet. Parameter problem, for example, when a packet with that is IPv6 is received by an interface which only mentions IPv4 or vice versa, and we will talk about redirection in a minute. In these error messages, in the data segment field of the ICMP message, we usually find the header or part of the header of the IP packet, the header of the IP packet that generated the event, plus part of the payload, for example, up to the first 8 bytes of data. So in this case, the interface which receives the notification of the event is able to understand what was the packet that caused this event. And since it's the interface that generated the packet, it is able to correlate the event with a specific packet. So let's look at some examples. For this is the case of redirect. So the redirect is used when we have a packet that is sent to a certain destination. It's generated by a host, and as you know, if the host don't have specific routes for that destination in a route table of the host, so if the destination was not say notified in any way to the source host, then the host will send the packet to the default router, and the default router will send then the packet out to the destination. It may happen that the host is connected to a network which has just one router, which of course is the gateway or the default router. So in that case, it's fine. So it's the only way to send the packet out to other networks, and therefore no action is taken. But it can occur that this local network has more than one router. So, for example, the packet that is going to destination A, which is first sent to the gateway, the default router, is then sent as a next hop by the default router to another router which is connected to the original network. The same network that is also connecting the source of the packet. So this is clearly inefficient because with a single hop, the source could immediately reach the correct router that is the closest one to the destination. So in this case, this router here that receives the packet from the destination, from the source and to the destination, will see that the next hop router is directly reachable by the source because both are connected to the same network as this router. So this router will generate a redirect ICMP message to the source. In the redirect message, there is an indication of what is the next hop router to use to that specific destination. So then, if this source will have to send other packets to the destination, the packets will be sent directly to that router and not to the gateway. Okay? So by this redirect message, basically this router is able to configure a new entry in the routing table of the host. And this is a possible way to automatically configure routing tables inside hosts. Okay. Then we are looking to a few examples in the message family, which has requests and replies, and in particular, so these are the most common types: echo request, address mask, router solicitation. But in particular, we only focus on the echo message. The echo message is a message that is sent as an echo request to a destination that can be either a router interface or a host. If the router interface, the destination router interface or host interface is able to receive this echo message, it has immediately to send back an echo reply to the source of the request, which is another ICMP message. So this is an echo request that is, for example, arriving here to this specific interface of the router. The interface will send an echo reply to the source, to the original host. So probably you have already guessed that this is a way to implement what is known as upper layers as the ping, the ping application, and we will look at it in a minute. So the echo message has different fields in the headers. There is an identifier which is chosen by the sender, and the identifier is repeated in the response in order to match request with response. And also, since more consecutive requests can be sent using the same identifier, we have also a sequence number, so that each response will also be correlated to the specific request, a specific request number in the sequence of requests. And then in this optional data field, the sender may decide to include a random sequence of information, for example, text or something like else. And if the receiver receives a request with this optional data with some information, the receiver is obliged to send in the reply the same sequence that was contained in the request. So in this case, the original sender of the request, when it receives the reply, can compare the original sequence with the sequence that was received by the reply, and this is a way to perform an end-to-end error check between the source and destination. If there are differences in this sequence on some bits, then it means that there was an error. And so ICMP is ICMP echo message is used by the ping application. Ping is the name of the application, and ICMP is the protocol that is used. And I think you are familiar with this application. You send when you send a ping to a certain IP address that is can be a router interface or a host. If the address is active, if the destination is active, is receiving the message and is allowed to reply, then it will reply with a set of replies. And you can see that actually ping does not send a single ICMP message, but a sequence of requests. And then you have the sequence of replies. From the replies, you can understand if there were errors. Of course, if one of these reply does not arrive, it means that there was a packet loss. But also you can check errors on bit by bit using the data sequences. And then you can also understand, you can also estimate the round trip time, okay? End-to-end round trip time by comparing the time the request was sent with the time the request was received. Okay, we will see this Wireshark if we have time tomorrow, but otherwise you can do it by yourself, maybe looking at this trace that is available on the BIP. So you can open Wireshark, upload this trace, and here you will find ICMP exchange sequence, right? ICMP message exchange sequence. Another application that is used ICMP echo messages is traceroute. Traceroute is an extension of ping, basically, that is able not only to tell if the destination is active or not, and the time it took to get to the destination, but also what was the route as a sequence of interfaces with their IP addresses, which was followed by the packet to arrive to the destination. And traceroute is based again on the ping message, and it's based on the echo request messages, so ICMP, with a trick. And the trick is to set the time to live of the outgoing messages to increasing values. So the first message that is sent by the source it has a time to live set to 1. Okay. So when the first message, that is an echo request, performs the first hop, okay, then in the next hop router, its time to live is decremented, and so the next hop router is forced to discard the message. The message, of course, has a final IP destination address, which is the host address, but it is discarded on the first hop. When the packet is discarded, a time exceeded ICMP message is sent back to the source. Okay. So the source can identify by this time exceeded ICMP message the interface that discarded the packet, basically the router that discarded the packet. Then another message is sent, setting time to live equal to 2. So it will go through the first hop, we make another hop, and it will be discarded. And upon the loss of this packet, another time exceeded message will be generated back to the source. So the source is able to identify also the second router, and so on and so forth until the message arrives to the destination. Okay. Then the destination, which receives an echo request, will reply with an echo reply. Okay. So by this trick, we can trace the route until the destination. And so basically you have all the list of all the interfaces that were crossed by the packet. Of course, this may happen. However, it's not so frequent, and especially it is true that you can have root variability, but usually it takes more time than the RTT, the typical RTT time. Okay? Before, of course, if you are unlucky, you can receive very strange routing return. Sometimes ICMP is not supported, it's not allowed actually on routers. For example, here in the Politecnico network, you cannot send ICMP messages, unfortunately. And so there is also the possibility of doing a trace route with UDP. Instead of sending ICMP echo messages, you can send UDP packets with the same technique, setting time to live in the IP packets that are hosting UDP segments to increase in values. In this case, it works the same. There is also another trick that is to set the UDP destination port to a value that is usually not used, so that in the last hop, when the packet is arrives to the destination is will discard the UDP segment, but it's obliged to send a port unreachable message. So that is so ICMP. Usually, what is not allowed is not all the ICMP messages, but only echo messages. So usually the error reporting messages are allowed. So it works with ICMP messages in return, but using UDP you overcome basically when the network is close to the echo messages. And here there is another case of another example of a Wireshark trace, where you can see a trace route session. So let's talk about ARP, which is quite important because it's fundamental for the forwarding operation, as we have seen. So this is a slide that is taken from the set about forwarding. Just to recall that we need an ARP table in each interface in order to associate IP addresses with MAC addresses in order to perform the direct forwarding delivery of IP packets, exploiting layer 2 forwarding capability of the layer 2 network. And so ARP is the protocol that allows to write entries into the MAC address, into the ARP tables. And how does it work? It is based on the broadcast addressing capability of the layer 2 network. Broadcast means that when we send a frame, a layer 2 frame, using a particular destination address, which is the broadcast address, the frame is sent to all the stations that are connected to the network. Okay. So the ARP table, which is basically a cache, stores IP addresses and corresponding MAC addresses. And when the IP interface has to send an IP packet to an IP address which does not appear into the current set of entries of its own ARP cache, then this interface starts to send an ARP request message. So the interface starts an IP protocol session. The ARP request is sent in broadcast, and it contains the IP address of the for which we are looking at a corresponding MAC address, and of course also the MAC address of the source, okay, of the source interface, so that the destination interface which is reached by this request can reply to the specific source. So this message is sent in broadcast. It derives to all the layer 2 stations that are connected to the network. Each layer 2 station has its own IP address. In the message, we have the IP address for which we are looking for the MAC. So all the stations that receive this ARP message start comparing the IP address which is contained in the message with their own IP addresses. And if a host recognizes that the address is its own, then it will send an ARP reply. And the ARP reply is not sent in broadcast, it's sent in unicast, because the receiver of this ARP request knows the identity of the source, the identity of the interface which originated the ARP request. So this is the scheme. So here we have the ARP cache of this interface of host B, which has its own IP address and its own MAC address. These are configured, so the interface knows this information, and the interface wants to have the MAC address which corresponds to the IP address of A. Okay. So the interface sends an ARP request that is sent in broadcast to all the interfaces that are connected to the network and are active. So it will certainly arrive also to host A. Host A recognizes the IP address which is contained in the request. So the request contains this information. Okay. The request is sent as a payload directly of a layer 2 frame. The layer 2 frame contains as a source address the MAC address of B, as a destination address the broadcast address. Okay, and the MAC that is used as broadcast is this one, which is again a MAC address with all ones. Okay, that is very similar to the broadcast address for IP. So this is the header of the frame, of the layer 2 frame, and the payload is directly the ARP message, the ARP request message. In the ARP request message there is the address, the IP address of B, which is the source, the MAC address of B, again repeated, which is the source. Then as a target there is IP address of A, and as a MAC target you have all zeros. So a string of zeros, because the MAC address is obviously unknown, is what we want to know. So when this message arrives to A sends ARP reply back to B, and in the ARP reply again we have an ARP message, reply message, which is directly sent, encapsulated in a layer 2 frame, and in the header of the layer 2 frame you will have the source MAC address, which is A, destination MAC address, which is B, and then in the ARP reply message there will be again the identity of B repeated, and then as a target IP address of A and the MAC address of A. Okay. So B gets the message and is able to copy this information into B MAC table. Okay. So now MAC table is available. When B has to send an IP packet to A, it knows where to find the MAC address. So basically this is ARP, and remember that while ICMP requires IP packets, so the ICMP message is encapsulated into an IP packet, which is then encapsulated into a layer 2 frame, the ARP message is directly encapsulated into a layer 2 frame. So it does not require an IP packet to be carried. Okay, about RARP, which is a reverse RARP, I don't stop. You can read some information. So this was the original method that was used for to get automatic configuration of interfaces, but it was then replaced by DHCP. So let's go directly to DHCP. DHCP is a message which is used to configure automatically interfaces. So why we would like to configure interfaces automatically? Basically, IP addresses can be assigned in a static way, but this, of course, requires a lot of work to directly configure each interface, especially when you have thousands or even hundreds of thousands of hosts that are active, interfaces that are active in a network. The alternative, which is more practical, is to use a server. Okay. If you have a server and a protocol that allows the IP interfaces to communicate with this server, then you can configure the interfaces in an automatic way. However, even if you have a centralized server, you can manage IP addresses in different ways that we will see in a minute. This is so if you are able to use a server, you can save on configuration operations, but you can also, for example, assign IP addresses in a dynamic way. And this is very useful, especially if you have hosts that are active only on a burst time, so they are usually inactive and then comes active for a short period. When you have so IP used for a limited exchange, or when you have a very variable host population. For example, in a Wi-Fi network, you don't know the MAC addresses of the host that will connect to the network in advance. So managing IP addresses in a centralized way does not always implies that these addresses are assigned dynamically. You can use the server to make a static association, so you have a list of MAC addresses stored in the server, and for each MAC address you have a static IP address that will be assigned to that specific MAC address when the interface becomes active. This is static association. You can do an automatic association, so this means that the MAC addresses that are allowed to interact with the server are always the same and a limited number. Each MAC address is registered on that server, but IP addresses are assigned not always in the same way, but on the basis of some algorithm. For example, you have a list of IP addresses and you assign them on a first come, first served based. Or the association can be completely dynamic. So you have a set of addresses, in this case usually smaller than the potential number of hosts. You don't know the host identity a priori, so maybe you have the hosts that are not registered. You just take a request that is coming from a host that became active on that network and assign an IP address. Okay? And this is basically the dynamic way that is usually adopted in Wi-Fi networks. This is an interface of a Windows system, operating system, and when you click on the automatic configuration of the IP address, it means that there is a DHCP server that is contacted and distributes the IP address. However, DHCP systems, you don't only provide IP addresses, but also information regarding the gateway and the DNS server. So DHCP is a richer protocol. So in dynamic association, of course, each time you have assigned an IP address, you cannot use it for another host. So the IP address is assigned to that specific MAC address. And this also implies that when the MAC address, the interface is not active anymore, the IP address should be released in order to be used for other possible users. And in this way, you are able to manage a pool of addresses which is smaller than the potential population of your users. So the DHCP protocol implies that there is a DHCP server in the network, and when the client, the interface becomes active, it starts to search for the DHCP server, and then they establish a connection. And since this is a sophisticated protocol, in this case, DHCP is defined on the application layer. So basically, it is an application layer protocol. And it's used, it has to rely on layer 4 protocol, that in this case is UDP, which then is encapsulated into IP packets and so on. So this is the sequence of messages that are exchanged from the client to the server in order to obtain the configuration. I leave this to you. It's not very difficult. You can go easily through that. This is also the complete scheme of messages that are exchanged. And you can have even more servers on the same DHCP servers on the same network. So the DHCP client initially contacts all the servers that are reachable on that network, and then it will focus on a single server in order to go on with the message exchange. You can also have DHCP servers outside your LAN, your network. In this case, you have to set up a DHCP relay device on the routers to the other networks. DHCP uses UDP messages, so UDP datagrams, and the initial message will have as a source address 000 because the sender does not know its own IP address. Destination address is broadcast, and since we are using UDP, we have also to specify a source port and destination port, and 68 and 67 are used as well-known port numbers. Okay, basically this is all. So tomorrow we will look at some exercises on layer 3, basically addressing and forwarding, and then we will start talking about routing next. Okay.
Scusa, solo una domanda veloce.